In this next segment, we are going to talk about how to predict the relative acidity of a solution made from a salt. So in your packages, you have this list of ions, and the answers are already given down at the bottom corner. However, what I would like for us to do is to take a look at each of these salts and go through the process of analyzing why we get the answer that we do. So if we take a look at example 1, we see that we have NaF, sodium fluoride. So when we analyze sodium fluoride, what you will see is that we have a salt made from sodium ion as well as a fluorine ion. The first question you need to be asking yourself is, where did the sodium and where did the fluorine ions come from? So going back to what we talked about before, these salts come from an acid and a base. So from this logic, where did sodium come from in terms of the base? And we can conclude that sodium came from NaOH. When we take a look at fluorine, we can conclude that fluorine came from an acid, and in this case it is HF. From our work, we know that sodium hydroxide is a strong base, and therefore the conjugate of that strong base, in this case Na, is going to have no desire to want to further react. Another way of analyzing this is that the sodium ion comes from group 1, and as we just talked about above, metal ions from group 1 will not hydrolyze. Now, when we take a look at the fluorine ion, we analyze it to come from HF. Now, when we take a look at the HF and take a look at our data chart, what we can see is that HF comes from, right over here, is a weak acid. And consequently, the conjugate base, in this case, the fluorine ion, is going to be a stronger conjugate base. What this means is that the fluorine ion is going to want to react with water. So going back to our analysis over here, we see that the sodium ion, because it comes from a strong base, will no longer want to further react with water. However, the fluorine ion, because it comes from a weak acid, is going to want to react with water. And so our analysis of NaF is going to be as follows. What would the fluorine ion do to water? As you take a look over here, the fluorine ion has a negative charge. That means it would want to take in a positive hydrogen ion. Where does it take the hydrogen ion from? It takes it from water. And so consequently, it reforms a hydrogen fluoride as well as a hydroxide ion. This hydroxide ion is now going to cause the solution to become basic. And this is why in number 1, when we take a look at NaF, it is going to undergo anionic hydrolysis, and the solution is going to become basic. Now, let's take a look at the second example. Once again, when we analyze sodium carbonate, we see that there is a positive ion and a negative ion. So the positive ion over here is going to be Na+, and our negative ion is going to be CO3 2-. Now, once again, when we analyze these two ions, we ask the same question. What acid and what base combine together to form the salt? And as above, we can conclude that sodium came from sodium hydroxide, and the carbonate ion came from HCO3. Now, once again, when we take a look at NaOH, we know that it is a strong base. And because it is a strong base, the conjugate, in this case the Na+, is no longer going to want to further react with water, and so it will not undergo hydrolysis. Or, as we analyzed above, Na+ comes from group 1, and because it comes from group 1, it doesn't want to hydrolyze with water. But when we take a look at the CO3, it comes from HCO3. Once again, we analyze the HCO3 from our chart. And as you can see down here, it is the hydrogen carbonate ion. Again, it is considered a weak acid. That means it's going to have a stronger conjugate base. And so, as a result, we can conclude that the HCO3 minus is a weak acid forming a stronger conjugate base of CO3 2 minus, and so the CO3 2 minus, or the conjugate, or the carbonate ion, is going to want to react with water. So the reaction of water is going to look as follows. This 2 minus over here is going to draw in a hydrogen ion from the water, and so you end up with HCO3 minus, and once again you produce a hydroxide ion. So as we can see, we again have an anionic hydrolysis, and we form a basic solution. Now in our third example, we have NH4Cl. So we undergo the same process. We break up our ion, and we know it's going to break up because according to the work that we have done in solubility, we know that anything combined with NH4 is going to dissolve. If you are not too sure, then once again, I encourage you to take a look at the solubility chart from the last unit. So the NH4Cl, the ammonium chloride, is going to break apart into NH4 plus as well as Cl minus. Now we analyze this. Again, we ask the same question. What acid or base combined to form this salt? So we can conclude that NH4 came from NH3. We can conclude that Cl came from HCl. So starting with HCl, HCl is a strong acid. That means the Cl minus, which is the conjugate base, is not going to want to further react. Whereas the NH4 over here comes from NH3, which is a weak base. Therefore, NH4 is going to want to react because it's a stronger conjugate acid. And so subsequently, we can analyze the reaction that is going to follow, whereby NH4 is now going to react with water. And in this case now, the NH4 is going to want to donate a hydrogen ion, and so it reforms NH3, and it forms a hydronium ion, and so our solution now becomes acidic. And so because NH4 is a positive ion, we call it a cationic hydrolysis. And our solution is acidic. Now the final question that I'm going to complete here is the NiNO3 bracket 2. So in this case over here we have Ni, and this is going to be 2 plus, and we have NO3 minus. Now when we analyze the NO3 minus, we know it comes from HNO3, and because it comes from HNO3, which is a strong acid, we know that the NO3 minus, or the nitrate ion, is not going to want to hydrolyze. Now when we analyze nickel 2 plus, we know that this does not come from group 1, and it doesn't come from group 2. So according to what we had stated above, anything that is not part of group 1 or group 2 may hydrolyze. So we are safe to assume that nickel 2 plus is going to hydrolyze or react with water, and when it reacts with water, it's going to form an acidic solution. Now the reaction that's going to take place, and this is the general metal reaction with water, is as follows. Nickel likes to have water surrounding it, and water being neutral is not going to contribute or take away any of the charges. And so in this case over here, there's going to be 6 waters that are going to be surrounding our nickel ion. Now in so doing, what happens is that one of the waters is going to lose a hydrogen ion. And so as a result, instead of 6 waters now, we're going to have 5 waters. And the water that lost the hydrogen ion becomes an OH minus. And so instead of a plus 2 now, because there's now a negative 1 charge, it becomes a 2, or it becomes a 1 plus. And in so doing, it releases an H plus. And so as a result, this positive ion allows for the water to give off a hydrogen ion. So once again, we have our cationic hydrolysis. And again, we form an acidic solution. So hopefully these 4 examples will allow you to examine the thinking process that is involved with the analysis of each of these salts and the kind of hydrolysis that they will undergo. There are many, many different salts that are present that you can examine, but the process of examining should be the same for all, and so therefore it will be a good idea for you to practice your analysis in the worksheets that are to follow.